Okay, thanks everyone. So I'm going to present on basically kind of a holistic overview of what I think are going to be the biggest challenges of really realizing this vision of turning actual residential neighborhoods into full-blown ISOs. I'm coming at this from a manufacturer point of view, so I'm also going to be presenting on our approach to actually solving some of these problems, what we have solved and what we haven't. So I apologize when I turn this, when I reformed this presentation, my dates all got misaligned, so it's a little bit off, but I thought I would start with a little bit of a history of inverter participation models. So, back in like the early 2000s, so the solar industry is still pretty young. So the standards that were written around grid interconnection agreements for PV were on a non-participation model. So basically the utility said that if anything goes wrong, they just wanted inverters to get out of the way, shut down completely. That they made official when IEEE 929 and 509 got synchronized with 1741. So 1741 said officially, we don't want you to do anything on the grid. And then in sort of like the 2007 timeframe, when I really started in this industry, the costs of solar PV to residential level were falling drastically, much faster than anyone in this industry ever participated. And that created really high levels of penetration, especially in certain states like Hawaii, where electricity costs are really high. And that created basically a really urgent need for more advanced controls that came faster than a lot of utilities were forecasting. Basically they kind of, a lot of places kind of rush to come up with new standards for, okay, how do we change the model for inverter participation so that we avoid some of these issues? And they kind of did them separately. So Rule 21 kind of forms separate of 1547. They're in the process of getting unified today with the next draft of 1547, which I think right now is still in revision. I don't know if it's made official yet. It's supposed to be official right around now with P1547, which will supersede Rule 21 and actually make it, now we're back to officially, we're requiring you to do things, not requiring you to do nothing. But really that's only the first step to realizing this vision of a inverter-driven microgrid controls, right? Because as we've seen, that these are basically integrating governing action into inverters, but still in a grid following mode, which means they're not designed to form their own grids right off the bat. They're just designed to support a grid that already exists. So what does the future hold? Well, future holds is, with a bunch of smart people working on the problem, like we have in this room, we can basically develop standard techniques so that in the future, islanding capability just becomes standard in all inverters. And this, I think a lot of people have had their own little picture of what the vision looks like. I like Brian's, I think, one of the best, so I was tempted to just steal his and put it in here, but this is mine. And this is actually my street. So I live in the little greenhouse right here. So this is what I vision as like, one of the first microgrids I want to build, because most of my neighbors already have solar. You can actually see it here. So my neighbor Marge has a big array. My neighbor Steve and Lydia have a big array. These people just installed Enphase. Good for them. I have a little array right here. So we already have a high penetration of solar, and we sort of all share one distribution transformer, which is right about here. So imagine if we had advanced controls on all of our inverters today. And we're kind of at the end of this long lateral. So we do occasionally get power outages, especially in the stormy season, and we're on well. So we lose our water when that happens. So if we were able to basically form a small microgrid when that happens, we can all run our wells, even if we have small power systems, because we're not running our wells at the same time. And the true vision would happen is if we're able to do this with a variety of manufacturers, right? Not everyone has Enphase. So the idea is that we develop sort of some standards that allow people to use some different technologies, but still allow them to interoperate with each other. So these are kind of a summary of what I feel are the biggest hurdles to adoption. One being safety. So how do we safely form multiple levels of islanding at a residential level and actually coordinate that islanding in a way that makes the utilities and the distribution system happy? Standardization and interoperability. Manufacturers can't support everything in the kitchen sink. It takes us time to write the firmware and to develop the controls to run on these inverters. So we basically have to develop more of a framework that leaves room for innovation but still allows interoperability. And that framework needs to be able to coexist with existing utility infrastructure as well. We can't basically invent a completely new form of controller that's not compatible with existing infrastructure, because utilities are not going to replace hundreds of millions of dollars of working control infrastructure. That doesn't mean we can't invent. It just means that we have to invent in such a way that can coexist with existing infrastructure, right? We can't basically replace the entire grid overnight. Communication security, that's a big issue right now. I know the DOE is looking at on this right now. Now that we're enabling all these complex features, if we design this like a cheap piece of consumer electronics, we're going to create a security hole you can drive a truck through. I know that a lot of our upper management loves the idea of asking Alexa to take the home off grid, but if we don't secure those APIs, then hackers will be able to basically reprogram your home to run at 600 hertz and just blow up everything in your house. So security has to be taken very seriously. And then last two, scalability. Basically we're going to get this exponential node increase in how many generation assets you have on your system. And that actually freaks the utility out. They don't want to basically extend their LMP marketplaces to all these nodes. So we have to be able to support some type of aggregation to support that scalability. And then compensation, and this is a problem already today is, how am I going to be compensated with providing all these ancillary services to the utility, right? If my inverter and my hardware is being used to actually provide the support structure, I should be compensated in a similar way to the power plants are today. So a little bit about our particular platform. So this is our IQ8 inverter. It's the next generation inverter that we're scheduled to release this year. It's based on our 7th generation hardware. So we actually didn't design new hardware for this. It's mostly new controls that we're embedding in this next inverter. Basically 295 VA steady state, 450 VA overload capability, which is a lot of power for us. It's probably a very, very small amount of power for most people here. 97% efficient, and this is the first inverter that has grid forming support capability in it. So we're actually going to be selling an inverter that has some of these controls embedded. So it uses in a very advanced form of droop control. It's sort of a combination of several different presentations I've seen here today. We've designed it to be stable under all load conditions. So the droop controller is designed so that it can be fully loaded and it can go to 0 load instantaneously and still be stable under all different kinds of linkage impedances. So it doesn't matter if it's on inductive lines or resistive lines. The droop controller was designed to be stable under those conditions. And of course, it's bidirectional. So we actually use the same inverter for our solar and battery product, just different firmware. It uses a distributed hierarchical control system, basically identical to what was invented in the early 1900s by the utility. So we didn't invent this, right? We got a lot of our ideas for how to implement these controls from a book that was published in 1966. But a lot of off-grid technologies that are sold in the residential market today use a master-slave approach, where you have one inverter dedicated as a master, and that forms a grid, and then it tells all the other inverters to what to do in basically a current injecting mode. That was not going to work for us, particularly because we use microinverters, right? So that master has to absorb 100% of the load instantaneously because of the limit of your communication system. Well, that means with a microinverter, right, we only have 300 watts of load pickup capability. That won't run that many appliances. And also, our installers weren't going to want to install high bandwidth communication systems on every single microinverter they're installing in the roof. So in order to do grid forming, we actually had to solve this in a distributed way. So we actually adopted right off the bat a hierarchical controller, same architecture as used by the grid, that uses primary, secondary, and tertiary controls. So the primary control is embedded in the DSP of every inverter. We run that primary control action very quickly. So this actually probably wouldn't be considered primary control action from the utility sense. This would be what some people have called fast frequency response or initial reserve. But for us, we just call it primary control because it's frequency and voltage based. It's 100% autonomous. And because it's 100% autonomous, it's very robust. It doesn't rely on any communications at all. I've run my house off primary control alone, and basically all my appliances are fine. I do notice small tone shifts in my record player because it's an old record player. It runs a synchronous motor, but it works just fine. Our secondary controller is based on our gateway. It's basically doing automatic generator control. We're actually using pretty much identical control that utilities do. So we calculate area control error just like they do using tie line bias. So we calculate the area control error and we broadcast once a second to zero out that area control error. So really we're using the same controller. We're just treating our little house like a small little utility area. And our ENVOY, our gateway, is basically the balancing authority for that area. So we're running sort of like a little mini utility on the house. And because we're like very compliant with the way the grid wants to do control as well. Tertiary control, that's what I'm working on right now. We're in the process of redesigning our energy controls in the house to actually operate like a little bit of mini balancing authority. So right now, our products today do things like time of use optimization, export limiting, but they're coded very simply. They're coded like a bunch of if-else statements, so it's very logic-driven. We're currently in the process of re-architecting that to run as a true marketplace. So we're actually going to run, even though we don't really have to, inside the house, we're going to run like a little microgrid. where every single one of your inverters is like an independent power plant that's bidding into this marketplace. And then the gateway is basically the marketplace operator, the broker for that marketplace, and sends rewards. And the reason that we're re-architecting this is because we want to make sure that we have an architecture that's going to be able to support hierarchical marketplaces in the future as well. So that's going to be, gateway driven, and we're going to use PLC multicast to re-optimize the energy flow on our systems. So our primary controller, like we said, we're using a very advanced form of Droop with virtual impedance. And this just shows a little diagram of me very temporarily, if anyone's from PG&E, pretend like this was just simulation, running grid forming controls on my house. Like I said, I'm at the end of a long lateral. So I actually have quite a bit of third harmonic in my grid. I was surprised by how much third harmonic the grid had. I was barely in compliance with the ANSI limitations. And I turned on the grid forming controls on a battery inverter, and two things surprised me. One is the THD in my house did improve because I was supporting some of the harmonics in that lateral, so I got better THD. And this is what really surprised me. I got a minor improvement in the efficiency of my inverter, very, very minor, which, I thought if I'm providing harmonics, you expect the efficiency of the inverter to decrease. But in this particular case, what happened is because of that third harmonic, it kind of flattened out the power curve a little bit. So the inverter actually was able to support that energy more efficiently. So there's really, it's a kind of like a win-win-win. And I think that's been a theme through a lot of people's presentations where grid forming controls are not just for running islands, right? These grid forming controllers can actually do a lot to improve the dynamics of the utility, even when we're connected to the main grid. We can improve total harmonic distortion. We can dampen out sort of these subcycle harmonics that the grid's struggling with today. We can improve power factors on transformers. There's a lot we can do with these controls. But new specifications are needed so people can do proper analysis on these controls. Different vendors are going to have different capabilities and techniques. We don't want to develop a standard that constrains innovation. So if we basically develop a new specification for how we want to describe these inverters that's really catered towards one specific type of design, you're going to hinder innovation because you're not going to allow people to use other forms of control. So how do we develop these techniques? First, I'll say inverters are not synchronous generators, so don't use that industry for inspiration on how to spec them. You would not believe how often we get the request for utilities to provide us the XR ratio impedance of our inverters, and I know for a fact that they want that number for short circuit analysis, and it's the wrong number to use for short circuit analysis because inverters are nonlinear devices. They're going to current limit. So please, don't try to spec an inverter like a synchronous generator. It isn't one. So my sort of proposal was that we should start including Bode plots in inverter data sheets. Because a Bode plot in an inverter data sheet would allow for a variety of different controllers and characterizing the dynamics of that controller in a standard way despite what controller you're using. So if you have virtual impedance simulation, if you have a PLL that introduces some impedances at different frequencies, a Bode plot would include all those dynamics, right? So the Bode plot would include the dynamics of your EMI filter, it would include your controller, it would include your PLL, all in one little datasheet item that can be used for a variety of different designs as well as a variety of different analysis techniques. So you can imagine that you could use this for transit simulation. You can also use it for more quasi-static simulation, like dynamic phasor analysis and such. So I'm not an expert here, but that's sort of my initial approach, right? Is a Bode plot and inverter data sheets. And as you can see here, this is our Bode plot. The solid blue line is the impedance that we're targeting, and the dots are what we were actually able to achieve with our control technique. So because of the speed at which we switch our power electronics, we're able to emulate pretty accurately up to 10 kilohertz. And around 60 hertz, you see that kind of resonance there. That's actually the droop control acting, right, at the fundamental. Okay, safe islanding. So like I've heard it mentioned a few times is that all these advanced controls can actually create large no detect zones. And algorithms for detecting islands are sort of tailor-made to very specific physics and usually a very specific manufacturer. So what happens if we mix different vendors and different system topologies? How do we avoid unsafe islands in these cases? One presenter made the comment is like, well, maybe we should reevaluate as whether or not we really need anti-islanding in the first place, because it's not like the utilities can shut down the main power coming from the other end. Why should we have to shut down the low voltage end as well? But we're not going to be able to change that off the bat. So we do need, I think, at least initially, a sort of universal approach for multiple vendors to work with mixed heterogeneous systems to detect when we're in an island that we're forming ourselves from the distribution end. Our approach has, and by the way, this is not what we invented. I first read about this in a paper in 2006. But the idea here is you create sort of this dynamic deadband that runs at a much higher bandwidth than your other controls. And in that deadband, you actually you run a destabilizing control. So you actually, and we're using a technique very similar to what's described in GEM1498, where they actually control VAR injection based on frequency deviation. So it still allows you to run droop, because as the frequency is changing slowly, you can still do like slow speed droop controls to help the utility with their primary control response. But in the event you form an island unintentionally, this will create very large frequency jumps that are very easy to detect. But because it's a deadband, it'll rail to a frequency and voltage deviation that's still acceptable for your own loads. So you can get a pseudo-seamless transition. So this shows an actual islanding event that we ran in our laboratory. And in this case, we were actually commanding a very large export at the time because we wanted to see, how good was the system at limiting the voltage and frequency deviation when we severed the grid at kind of the worst possible moment, meaning that we were exporting a ton of power, both real and reactive, and all of a sudden the inverters had to curtail very quickly to avoid an overvoltage event. And this is our actual transient response. So this is the transient response of our primary regulation system with our anti-islanding. So you can see that we're able to converge within about 1.5 cycles with very little overshoot and a very nice transient response. Interoperability. Our idea here is that we can use our secondary controller, sort of an abstraction layer, for working with different types of governing actions from different controllers. And we actually have to do this right off the bat anyway to be compliant with things like Rule 21 and 1547, because our droop control that we're using for instantaneous balancing when we're islanded is not compatible with the governing action described in those standards. So how do we make it compatible if we're actually forced to be compliant? Well, we actually use secondary control for that. So the idea is that, we are running ACE equations, just like a balancing authority would run. When we're off grid, we just set the intertie schedule to 0, right? If your home is islanded, then you're not going to be able to export to the grid. So we're not actually changing the control. All we're doing is we're saying that, okay, if we're off grid, you set the timeline you set the intertie requirement to 0, and your ACE equations will actually only be based on your voltage and frequency error, and the system naturally regulates voltage and frequency off grid. When you're grid tied, you can basically set your intertie schedule based on the frequency watt and volt var curves that you're required to for Rule 21 or 1547. And then in microgrid mode, there can be some upstream controller that's basically giving you a tie line bias schedule, very similar to the way balancing authorities work today. So it's one controller in all cases. We're kind of using that. We're using the area control error technique as an abstraction layer to work with any form of inverter control, as long as it's droop based, right? Scalability. So, like I said, this problem was actually, we feel, solved in the early 1900s because tie line bias control is a recursive control technique. It supports aggregation of resources at each level in the area. So utilities today have areas within areas within areas. So they actually already support aggregation. So they don't have to extend their LMP marketplaces down to millions of devices and home, right? Homes can basically run their own internal marketplaces. They can create aggregated bids for an entire house that bid into a neighborhood market. That neighborhood market could be operated by some DSO that could aggregate all those bids into the actual LMP market. So we can get, when we're running hierarchical control in these techniques, we get aggregation at multiple levels, which solves the scalability problem because each actual controller marketplace is actually only handling a fixed number of nodes. Security, I'm not an expert here, so this is going to be the very condensed version of security. If you want to learn more, I can refer you to our security architect. I have a couple just headlines here showing security is an issue today. So these systems, now that we're enabling all these advanced controls, they become very attractive for hackers, right? Right now, if, most energy systems just allow to get telemetry, which isn't that interesting. As soon as we enable the ability to control power flow from homes remotely, we have to make sure that those are secured, or else we basically open up a whole new world for hackers to attack the power system. A lot of new attack vectors. So Scientific American, Reuters, PV Magazine, all are saying that, smart inverters, if they're not secured, could create a huge problem. So very brief version of our approach, really securing the design is really one of the first step in a 4-tiered approach. So if you secure against all known design attack surfaces, you make a system harder to hack, but not impossible. There's nothing that's impossible to hack. So creating a secure system is really, in our mind, a 4-tiered process. So 1 is secure design, securing against the known attack vectors. Step 2 is a strong identity infrastructure so that you can authenticate where these commands are coming from. And that's actually required in 23.5. So 23.5 did a great job of incorporating that into the standard. Deep defense, so adding additional security measures at each level in the control hierarchy. So this goes all the way down to primary control. So like our primary controller has sanity checks on the commands that are being sent to it, so that if there's a command that's sent that doesn't pass a checksum or it exceeds values that it's expecting, they get thrown away. So basically, you have to really take a multi-tiered approach so that if one layer gets hacked, there's still multiple tiers to protect you, and really you're just isolating the hack to one part of that system. And then last is auditing. So this is an ongoing process where we actually monitor for traffic on the system that's suspicious. And this will actually be part of an organization. So a whole new organization to monitor basically how people are using your systems and authenticating the use of those systems to make sure that they're valid. Compensation, like I said, this is the area that I'm actually working on now at Enphase. There's a lot of different, so people call this transactive energy, where we're trying to basically create a more universal approach to running these marketplaces that work all the way down to the homeowner level. And there's a variety of different technologies out there. There's Power Matcher, there's the Energy Web Foundation, which is working on blockchain-based marketplaces. There's also control frameworks. There's a lot of people from PNNL here. So I use Voltron a lot. Great job. Extremely well architected framework, so thank you. Data models and standards, 23.5, Sunspec, OpenADR. So really, you can get lost in all these technologies. How do we build a universal transactive framework out of these technologies that everyone can get on board with? So our approach has really been, I think someone said that marketplaces should be customer driven. I really like that, because that's kind of what we're doing in our own system, where we're actually the customer and the designer at the same time. We're actually developing an intra-system marketplace on our Envoy. So we want to run our energy controls internally, even though we own all the equipment. We actually want to run the controls on them sort of like a blind auction marketplace. So we're actually having to develop this marketplace right now and developing the data models for that. And our idea is that we're going to support existing standards by just creating an abstraction layer on top of that marketplace. So for example, 23.5 basically has this idea of sending price signals down, right? Well, and really, that's just a bid. That's just a marginal price bid from the utility. So we can convert that price signal from 23.5 client into an ESP agent bid, right? So that's an energy service provider bid. And we can actually start supporting this on our own marketplace. So we're actually going to be creating a proposal for a market participation model that solves our problems. So we're having to figure out how to make this work today on our own systems. And how do we support things like probabilistic forecasts? How do we support startup costs for resource, ancillary services, and actually draw up a true microgrid control system to make sure we have enough reserve in the system to run it stably for our own system. And once we have that working, then we want to start open sourcing that. It's basically going to IEEE and said, okay, here's a market participation model that we designed that works, and we've tested it on our systems, and we think that this could be adopted into something like Sunspec or 23.5. Quick slide about blockchain. I've actually written code that sits in the blockchain today, so I have a lot of experience. I've written in Solidity. I've taken classes on this because I wanted to learn really how the technology worked. In my opinion, there's still significant hurdles to adoption on using blockchain for marketplaces. If you want to learn more, I recommend going to the Energy Web Foundation website. In my mind, Energy Web Foundation is making the fastest progress towards how to modify blockchain technologies and use them appropriately in an energy marketplace. But even they'll point out that the Ethereum virtual machines is not well suited to energy markets. It's inefficient at executing code, so that limits the sophistication of your application. Solidity is a custom programming language they invented, so there's very few developers. It's a pretty simple language, but still, it's not as old as other programming languages, so you're not going to have as many libraries, you're not going to have as many developers, you have to code everything from scratch. WebAssembly is a promising replacement, but that's still young as well. Cryptographic currencies are very volatile. Most people are going to be very reluctant to trade energy in a cryptocurrency. And if you want to use cryptocurrency as an abstraction and basically transact in real currency, it requires something called an oracle, which is not distributed. So what's the point of having a distributed consensus mechanism if you have a single point of trust to get data in and out of the outside world? And the same problem exists with getting data from sensors and devices, right? what prevents people from hacking their meter? So if you have your meter that basically says, here's how much energy I injected into the system, and it goes into the blockchain, and you advertise it as being this distributed consensus that's completely trustless, it's not true, because data has to get in and out of the real world, and that real world is hackable. So there's still a lot of problems to solve. A few closing thoughts, getting here to there. Don't treat the utilities as like the enemy. They have a lot of their own frameworks and marketplaces, and they work really well. You can learn a lot from existing control systems. And they're going to be very reluctant to change things that work really well today. Like our lights, I have not seen any power outages during this presentation, so they have control systems that work pretty well. And so we really need to figure out how to work within frameworks so that we can transition into an inverter-driven microgrid. And in my mind, really a market for true DSOs is needed to bridge the gap between prosumers and utilities. So we need to basically develop technologies that enable new businesses to form that allows DSOs to operate profitably. Right? Imagine if a new company came into your neighborhood, bought up all the distribution assets and said, hey, we can operate the system more efficiently, we can charge you less money for electricity, and the utilities will like it because now you have this asset that's bidding very efficiently into their LMP market, and they don't have to manage that distribution system. There's a lot of money to be gained there. I can tell you right now, about 65–70% of my electric bill is distribution costs alone, not generation. So there's a lot of low-hanging fruit into improving the efficiency of our distribution systems using these new technologies. And in my mind, what's needed to really kickstart that model is just kind of us. Like the manufacturers need to basically develop technologies so that these businesses can actually operate. We need to develop the tools for them to do that. And a quick picture from my little microgrid test system. So this is my house. My wife and her vows sort of foolishly allowed me to run energy experiments on our light. So I did not tell her we were off grid. This particular picture I was trying to test how many inverters could run my full-size fridge before my Wi-Fi router. And the experiment was my wife was watching Netflix. So when she complained our Netflix stream dropped, I knew my Wi-Fi. And I was surprised, actually. So really good overload control can actually do a lot in this. So I have a lot of interesting observational data from my little microgrid test system that I'm happy to talk to you more about afterwards. Thank you.
Thanks, Donny. Very fast hand there. Excellent presentation.
Thank you.
So first off, your wife's behaviors in the protection industry is called a trick flag. So big LED that says you just tripped.
So I'm trying to figure out the marginal cost of her comfort level so that I can bid that into the system.
That's awesome. So the next clarification would be that the X over R ratios are used to determine the breaker sizing most commonly, because what you're looking here is DC offsets and rain down. Thirdly, the X, the impedance, is most important in their perspective for time coordination stuff. So there's different reasons they're asking for X over R versus X. Mm-hmm. But otherwise, wonderful.
Yeah. So quick note, you actually, interesting thing about running hierarchical control is actually you can run different X over R ratios in different tiers. So you can imagine that when you're running islanded, you may want to match the X over R ratio of your Juke control to the governing action of your loads, because then your governing response is orthogonal to your load governing, so you can limit how much voltage and frequency deviation you get. When you're grid tied, you usually want to match that X over R ratio of your secondary control response to the impedance looking into the grid, so you can actually optimize your voltage regulation. But the nice thing about it is your secondary control in that hierarchy, you can actually change those ratios at different levels.
Thank you for the presentation. So I have two questions. So how you make sure that the anti-aliasing control exists with inverter control?
So I'll go into a little more detail on that. So the idea is that we create this band of operation around 60 hertz where we're running very high speed, bad behavior, like destabilizing behavior. And the idea there, and as soon as you exceed that dead band, we go back to our high-speed troop control. So what happens is that in the event we form an unintentional island, we quickly go to either the plus or minus side of that rail. So if we're currently producing more power than our loads, we go up to high voltage and frequency. If our loads are consuming more power than are currently generating, we drop to low voltage and frequency. And we design that dead band to be large enough to be very easily detectable, but small enough that it's still tolerated by loads for that short duration, because it takes us time to disable that. So for us, I think we set it to like plus or minus 2 hertz or something like that, but it's completely programmable. And it gives us a really very nice detection band, but still providing an envelope on when you form an island that wasn't predicted or forecasted and your inverters aren't told ahead of time. It sets a band on how wide the voltage and frequency can get. So you get this pseudo, I don't call it seamless, it's pseudo seamless, because you do get a jump in voltage and frequency. Well, you still have low speed voltage and frequency regulation to meet Rule 21 and 1547, because we're talking about control in the tens of milliseconds, right? In the tens of milliseconds, we're running basically a VAR injection technique based on deviation in frequency. So it's dynamic, at very high speed, that basically is able to operate fast enough that even with those other lower speed droop controls, it's still able to destabilize the system.
Well, and thank you again, Donny, for a really interesting presentation.
Thank you.
So we get Brian to do the last presentation of this morning.